I'm Felicia Chow, Public Affairs Officer, and we've got an exciting panel for you today. We're going to be talking about how asteroids relate to the origins of our solar system, our search for life, and what NASA is doing. Now, I'm sure there might be some overlap in what you've already heard before, but I'm sure that's also going to be very, very eye-opening, at least what we're going to be covering in our panel. So today, our panelists are Ellen Stofan, NASA Chief Scientist at Headquarters, Michelle Thaler, Deputy Director of Science Communications, also at Headquarters, Alex Young, Heliophysics Associate Director at the Goddard Space Flight Center in Greenbelt, Maryland, and Lindley Johnson, Planetary Defense Officer at Headquarters. And with that, Ellen, can you start us off with how asteroids relate to the origins of our solar system?
Sure. It is such a pleasure to be here today. It was such a pleasure this morning to see that rocket roll out to the pad. We're really going to an asteroid tomorrow. This is incredibly exciting because if I can have the first video queued up, you know, asteroids like Bennu, the information we're going to gain from OSIRIS-REx, it's really going to help pull back the curtains on the origin of this planet, on the origin of life itself, and we're going to be talking about that here this morning. Now, Take us back here now to about 4.6 billion years ago, when at this point, shortly before the formation of the sun, what you had was a cloud of basically gas and dust like you're seeing in this video. So just think, everything that you're made of, your cat is made of, this building is made of, all of that, a little over 4.6 billion years ago, was just part of this cloud of gas and dust. Then probably there was a nearby star explosion. The shock waves from that came in, disrupted that material. The material collapsed, and the sun formed. And around that early sun was this cloud of, now most of the mass from that collapse went into the sun, but the material that was left formed basically a rotating disk around that early sun, and that's called a protoplanetary disk. If I can have the next video. So again, now think, 4.6 billion years ago, most of the mass has gone into the sun. And how do we know all this? Well, we have telescopes like the Hubble Space Telescope that's now able to look at all these different stages of solar system formation, not our solar systems, but other solar systems that are forming. Now that dust, as it's in this protoplanetary disk, it's colliding. Those collisions are now producing bigger and bigger grains, then clumps of material, and then ultimately forming planetesimals, which collide and form planets, and that's where the Earth came from. Now, but not all of that material got swept up into planets. Some of it was left over. That's asteroids, that's comets. So studying these materials are incredibly important because it is this fundamental building block material that the rest of the solar system is made of. And given that we really only have samples right now, we have a few samples from Mars, we have a lot of samples from the Earth, we have samples from the Moon, but we really have sampled such a small amount of the material in this solar system. If I can have the next slide. Now, what we've been doing, obviously, is trying to understand what is this material that we're all made of. We have meteorite collections to study, and from that we've learned not all these materials are the same. You've got stony meteorites, you have irons, you have carbonaceous chondrites like Bennu. This is the asteroid Ida. It's about 59 kilometers across. This is an image from Galileo. This is just one type of asteroid. It's a stony asteroid. It actually even has its own moon called Dactyl. And this cratered surface, kind of potato shape, is kind of how I think about asteroids when I think about what they look like. But this is just one type of asteroid. If I can have the next slide. This is Itokawa. It was imaged by the Hayabusa spacecraft. And you can see it looks very different. The materials aren't actually all that different, but instead what you have here is basically a rubble pile. You've got very loosely consolidated material that is extremely interesting in how it formed over time. You also notice it has this very unusual shape. It's what we sometimes refer to as a contact binary. It looks like two different large pieces of material have come together. And some of you might think it's very reminiscent in shape, but also in appearance, to the appearance of the comet that's has been studied for the last several years by the Rosetta mission. Now, again, there's different types of materials that are occurring, different types of rock. But one thing we do know is that the rocky asteroids, we used to think that a lot of the water on the Earth was brought to the Earth by comets, but over time we've actually figured out that we think most of the water on Earth was actually brought here by asteroids. That's part of the reason we like to study them. Now, most of the asteroids in the asteroid belt, like the ones I've been showing you, most of those are fairly rocky materials. If you go out to the Kuiper belt, everything is much icier. Just think about Pluto. The other Kuiper belt objects are like that, much more made of the ices. And Michelle's going to be talking a little bit about why there's this difference in composition between the inner belt materials we have and the outer solar system materials. The next slide. But one of the most important things that we've been learning is that asteroids aren't only a key to the building blocks of what our planets are made of, and then therefore they help us understand the very early history of the Earth, how the Earth works. We've also discovered organic material in asteroids. And you can see in this image, there's things like adenine, guanine. If those of you who don't know what those are called nucleobases. These are the letters that make up our DNA, that make up our RNA. But the really cool thing is, we haven't just found the letters basically of our DNA in meteorites. We've found other letters that life here on Earth doesn't actually utilize. Now that's really cool, because again, this material is being delivered not just around our solar system, but around our galaxy. And there's different letters out there. So when we start thinking about life on other planets, we really start wondering, what could that life be like? Is it different than life here on Earth? Could it be utilizing some of those other letters? We don't know, but that's what we're trying to figure out. Michelle?
Well, thank you. Yes, the context of asteroids is just really incredible. And in fact, I have a carbonaceous chondrite here in my pocket, which is probably not something you hear a lot of people say. So this is a meteorite sample. It's a sample of the very, very primitive type. Primitive, but I mean, it's hardly been processed at all. This little sliver of something is actually a bit older than the sun. And it has all sorts of stuff in it. It has more different kinds of organic molecules than you find in my body. It has more nucleobases than you find in my DNA. And if you want to, okay, y'all are going to promise to give this back, right? Whoever gets this, right? If I pass it around. So if you look at, there's a little inclusion in here, which is one of the first solid pieces of our solar system. That's real, right here. So you can pass that around. There you go. All right. So there's your carbonaceous chondrite. So if I could have my first graphic. The thing that's amazing to me, okay, why do we need the story of comets and asteroids to really figure out why life started here on Earth? And this is something that at NASA, you're hearing today from us about some of the large strategic priorities of NASA science. And one of the things that I'm involved in is the study of exoplanets, planets around other stars. And as of today, as of this morning, because I actually went and checked, there are 3,375 confirmed exoplanets. And we're following up on almost 5,000 more candidates. And all of a sudden now, it's not just an example of one solar system. We now have a statistical sample of how many solar systems evolve. And one of the things that we see is that where the Earth formed around the sun, as close as we are to the sun, you find very, very little water. Very little of what we call the volatile elements or compounds, things that are easily evaporated, things that don't survive under warm conditions. And this is an artist's conception of a young solar system where what you're seeing is that the young star has basically either blown away or heated up all the material close to it. And you need to get out to a certain distance away where it's cooler in order for these ices to start condensing. And astronomers call this the snow line. And in our solar system, you really don't reach the snow line until you get out towards the orbit of Jupiter. So where the Earth formed, things were very dry. And the Earth is a rocky, solid body that formed largely from compounds that you would find in that place. But where did all of the stuff that makes us up come from? And this is where the story of asteroids really comes to the fore. If I could have my next graphic. You may have heard that nowadays we're actually trying to piece together how the early solar system was affected by the formation of the planets and possibly even planets moving around. There's a current hypothesis that Jupiter may not have formed where it is right now. It may have formed a little farther out in the solar system. It may have moved in, almost as far in as the orbit of Mars. Currently, we have the Juno mission that has just arrived at Jupiter. And one of the scientific goals of the Juno mission is to look at the chemistry of Jupiter and look for clues as to where Jupiter formed and where it may have migrated. So Jupiter moved in, we think, probably past where the asteroid belt is now. And that probably disrupted anything that was there. We believe that almost all the material that was originally in the asteroid belt has either been thrown into the inner solar system or thrown out of our solar system entirely. And this amazing era was called the era of heavy bombardment. It happened many billions of years ago. But this is an artist's conception of the idea that throwing in these asteroids, throwing in these comets, Eridani, there is an asteroid belt nearly about where the asteroid belt is here. It's about 3 astronomical units, 3 times the Earth's distance away from the sun. So already we know of other solar systems that have something like our asteroid belt. And there's even a farther out belt around Epsilon Eridani that's more like our Kuiper belt, where we find comets. So in our exoplanet program, and in the program where we're going to start looking for signs of life, not only in our solar system, but even around other stars, we're trying to piece together the equation of where would it be likely to find life. And perhaps one of the things that's in the positive column, a good place where life might exist, is a place with asteroids. An asteroid belt could have delivered the water, the organic molecules to the inner solar system and made the conditions right for life.
Thank you, Michelle. So Alex, why don't you tell us about how asteroids can give us the history of our solar system?
Yeah, so one of the things that's really interesting is asteroids are traveling through space, and space is incredibly dynamic and very hostile. And the reason is because of the sun, mostly. The sun is putting off this constant stream of particles. If we look at the next video, you can see the sun's outer atmosphere is incredibly hot, millions and millions of degrees, so hot that it streams away and it carries off particles, it carries off electricity and magnetism, and this is traveling through the solar system in something we call the solar wind. And it's bathing all of the bodies within the solar system. And these are, as actually Danny mentioned last time talking about ionizing radiation, one of the things is this is ionizing radiation. So this is radiation that penetrates much farther than just UV light. And it's hitting planets, it's leaving its mark wherever it goes. We can see it here, it's going to pass Venus, and you can see it hitting the surface of Venus because it doesn't have a strong magnetic field. And this is the same situation that we have with an asteroid. So as an asteroid is traveling through this incredibly dynamic space, it's being bombarded over billions and billions of years, and it's leaving its mark, basically recording the history as it travels through the solar system. But the interesting thing is that there's a little more to it. So that was the solar wind, which is constantly streaming away, but the sun also has this ebb and flow of activity, going from periods where it's extremely active, throwing off big blobs, billions of tons of solar material, huge blasts of radiation, and this is happening on top of what's happening with the solar wind. But then, when the sun is not active, this actually allows another form of space weather to come into the system, something in the form of galactic cosmic rays. So when the sun is active, it pushes those cosmic rays out of the solar system, but when it's calm, it lets those in. So then we have this other component of energetic particles of energy that is bombarding these asteroids. And so over time, we're seeing this history of the change in the solar system, the change in solar activity, the change in the environment. And this is really important because understanding how the sun has changed over time or how other stars have changed over time is critical for understanding the formation of life, because we believe that not just water, but the activity of the parent star has a huge role in the evolution of life and the evolution of solar systems, both here and throughout the universe.
Well, thanks. Well, speaking of the sun, how does the sun affect the trajectory of asteroids?
So the sun has another area where it causes a little bit of trouble. If we look at the next graphic, when an asteroid is rotating, just like a planet, it has a day and a night. And when it's experiencing the day side is getting heated up from the sun. And then as it rotates to the night side and cools, that radiation that's leaving the asteroid creates a very small force. And that force, depending on how the asteroid is rotating, can either speed it up or slow it down. And for smaller asteroids, this can have a huge impact over time on the trajectory. So we've come to find that we can't just determine where the asteroid is going to go just by normal orbital dynamics. We have to account for this Yarkovsky effect, which is due to the heating and cooling from the sun.
So we've heard a lot about how the sun can affect the trajectory of asteroids. So Lindley, why don't you tell us about what NASA is doing to track and study asteroids?
Okay, well, you've heard all about formation of the solar system and all the material that's left over from the solar system, and the planets, including Earth, getting bombarded by this material and it being the creation and probably the creation of life. So where is all this matter now, and is there any hazard to the Earth being hit in the future? All that is the job of the Planetary Defense Coordination Office at NASA and the projects that we have for surveying the solar system and finding where the asteroids and comets are. If I could have the first animation here. One of our projects is the NEOWISE. It's a spacecraft that's in Earth orbit, and as Earth revolves around the sun, it sweeps out the population of asteroids. Now you clearly see the main asteroid belt, the gray dots, beyond the orbit of Mars, and I need to say that objects in this animation are very, very much smaller than they appear here on the animation. In fact, you wouldn't be able to see them at all if we had them the size relative to the orbits. The depictions in the movies are just, totally not correct. Star Wars and Star Trek Beyond, they go into these asteroid fields, and these asteroids are all around and bouncing off of each other. Well, we've shown in the Juno mission, in the Dawn mission, has spent several years in the asteroid belt, and you can go through the asteroid belt without seeing a single asteroid unless we direct you right to that asteroid. So you see here the main asteroid belt, and then you see these objects that have entered the inner solar system there in the green. These are the near-Earth asteroids, of which the asteroid Bennu is one of them. Bennu, as mentioned previously, was discovered by one of our projects, the Linear project, back in 1999. Could I have the next graphic? So we have several survey projects that are discovering, tracking, and characterizing the near-Earth object population. NEOWISE is our one spacecraft. This is actually a repurposed spacecraft. Its original mission was for astrophysics and mapping the infrared sky, but we saw, as we compared image to image, we could discover the asteroids moving through those fields, and it made a very good asteroid hunter. So after it completed its astrophysics mission, we recruited it as an asteroid hunter, and we've been operating it for 3 years now in that mode. Also, we have several ground-based observatories. The Pan-STARRS Observatory project in Hawaii has discovered a good number of the population of near-Earth objects that we know about now. We're about to, by the end of the year, we will have some 15,000 objects in our catalog. The Linear project, there in the middle, kind of a faraway view, but you kind of see the kinds of terrain that these observatories are on. The Linear project was the project that discovered Bennu back in 1999. And the Catalina Sky Survey there on the lower right has also done a lot of the discoveries in the catalog. And in fact, Catalina Sky Survey just early Monday morning discovered an object that had not been seen before, catalog 2016 RB1, and just right about now it is on its closest approach to the Earth, passing underneath the Earth at about 21,000 miles. That's closer than communication satellites orbit the Earth, but it is passing underneath the Earth, so it's not a hazard to any of those spacecraft, and it's not a hazard of hitting the Earth. But what observatories can see it actually before and after it passes underneath the Earth, because in the southern hemisphere we don't have too many observatories that work on this. We're taking as much data on it as we can. It's a very small asteroid. It's only about 10 meters in size, according to looking at its brightness. So if it were to have impacted the Earth, it would have disintegrated in the atmosphere. Could I have the next graphic? So we detect these objects that come close to the Earth on a regular basis. Most of them will pass by harmlessly, but we're looking for one that might cause us more of a problem. Back in October of last year, the Pan-STARRS project discovered an object designated 2015 TB145, which was a fairly sizable object. Turned out to be about 600 meters, 600 meters across. And the first images that we got of it that you see up there on the left, it was close approach to the Earth was on Halloween Day. So seeing these images about Halloween time kind of startled us a little bit there. If you have a little bit of imagination, you can kind of see a ghostly image there. That was imaged by the Arecibo radio telescope in Puerto Rico. We also got radar images using our Goldstone Deep Space Network telescope in California, and also spectrometry from the infrared telescope facility in Hawaii that determined that this object was probably actually the dead nucleus of a comet where all the volatiles had been exposed and burned off by previous close passages in the inner solar system. But we got more detailed images, next graphic, of the object using Goldstone as a transmitter and the Green Bank radio telescope as a receiver. We have detailed resolution down here to about 4 meters in size. And you see these bright spots on the surface of the asteroid, and these are determined to be, these are boulders that are sitting on the surface of this object, several meters in size. So what might we do if an object were discovered on an impact trajectory with the Earth? That's another area of research for the Planetary Defense Coordination Office. If I could have the next graphic. One of the projects that we are working on in collaboration with the European Space Agency, this project has just completed its concept studies and is ready, if the decision is made, to go into further design. The Asteroid Impact and Deflection Assessment mission, where the European Space Agency would build the rendezvous spacecraft called the Asteroid Impact Monitor that would go out to this candidate asteroid called Didymos, and this is actually a binary asteroid system, asteroid that's about the size of Bennu, a little bigger, that has its own small moon of about 100 meters across that orbits it. The AIM spacecraft, the Europeans, would characterize the system in those two bodies, and then the NASA and the U.S. would launch the double asteroid redirection test. This is a kinetic impactor that would impact the moon of Didymos, which we affectionately refer to as Diddy Moon, and demonstrate how much energy could be imparted to that body and change the orbital period of the moon. And this way we were able to test the effectiveness of this kinetic deflection technique that is thought to be one of the technologies that we could use to redirect an asteroid were on an impact trajectory if we found it enough years in advance. Another concept that we're working with is with the Asteroid Redirect mission of the Human Exploration and Operations Mission Directorate. They are working on technology that will take us to Mars in the future, particularly solar electric propulsion, and the ability to move large masses around the inner solar system like habitat modules and cargo. If I could have the next graphic. The asteroid redirect mission is of 3 major components. The identify component is done by the NEO observation program, the Planetary Defense Coordination Office, and that's finding good candidates for this mission. We have one that has been being used in the design of the asteroid redirect robotic spacecraft. And so that redirect part of the mission would be done by this robotic spacecraft, which will go to this candidate body 2005, or 2008, I'm sorry, EV5 is the candidate we're working with right now, but we're continuing to look. We might find a better one before the mission is launched. It will go and to the surface of the asteroid to collect a boulder, and then the crewed mission will bring that boulder back to lunar orbit, and a crewed mission will go up to sample it. If I could have the video of the ARM mission concept video. This is the solar electric propulsion spacecraft going out to the parent asteroid. It has these landing legs and these grappling arms, which will go down to the surface, but first of all it will survey the surface for a period of several months to select the best candidate boulder to retrieve. And then once the investigation team has decided which boulder is the best to retrieve for the mission and bring back to lunar orbit, it will slowly approach the surface of the asteroid, land down on those legs, and if these grappling arms that have these appendages at the end that are very much like a bunch of cat claws, or cats in this again, that these tines, they go down and grip the boulder, and actually these 2 grappling arms will lift that boulder up, and then the spacecraft will depart the surface of the asteroid, but before it leaves and goes to lunar orbit, it will do what we call an enhanced gravity tractor, and this is another technique for diverting a asteroid from its natural orbit. Just the mass of the spacecraft and this several tens of ton boulder, as you station keep to one side of the asteroid, nature's natural gravity rope, nature's natural tug rope, I should say, gravity, will pull that asteroid off its natural orbit. And then the spacecraft, after we've demonstrated that, will come back to lunar orbit, and the astronauts will go up and retrieve samples and return them to Earth. So already we have 2 techniques that are in concept and an entering demonstration phase for viable techniques to divert hazardous asteroids. Felicia?
Thanks, Lindley. So before we open it up for questions, and I'm sure you guys are dying to ask questions, Ellen, do you have any closing remarks?
Sure. So obviously we're all here to see what we consider to be a planetary mission launching to an asteroid, to understand that basic material. What is the asteroid made of? What can it tell us about our own origins? But in talking here today, you've been hearing how it's connected to everything that we do at NASA, from helping us to understand the possibility for life on extrasolar planets, for helping us understand what the conditions are in solar system formation that can lead to the habitability of a planet. We've heard about how the sun is so critical to the formation of life, the evolution of life, and yet it also influences what materials we even have on the surfaces of bodies. And then, of course, it's always the human consideration. How do these asteroids potentially affect this planet in the past and in the future? So while sometimes we think of NASA as being these different organizations out answering lots of different questions, those of us within NASA really see the connections between what we do, whether it's Jeff Williams landing last night after his record amount of stay in space over his career. He's getting us ready to go to Mars by helping us understand how humans can survive for long duration in microgravity. That's connected to everything you're hearing today, because we want to send humans to Mars because we want to go find out if life originated on another body in our own solar system. So from OSIRIS-REx to the work we do every day on the International Space Station, to the Curiosity rover, to the Hubble Space Telescope, to our future telescopes like James Webb, we're really trying to answer this fundamental question. Where did we come from? How did this planet form, and how is it going to change over time? And are we alone? So thank you all, and we're ready to answer questions.
Thanks. Now we're going to open up to folks in the room. So for those who want to ask questions via social media, please submit the questions using the hashtag AskNASA. Now, let's see. Hand over there.
Hi. This question is for Dr. Young. Also, awesome shoes, by the way.
Thank you.
Those are great. So you said that the sun can influence the motions of asteroids like Bennu through the Yarkovsky effect, which is heating and cooling. Can it also affect their motions through its outbursts, like solar storms, CMEs, things like that? I mean, those are obviously much bigger events. Can they move the asteroids around?
Well, more than likely, no. I mean, we don't know for certain, so I can't say exactly. But one of the key issues is that basically what's coming off, not thinking about the charged particles, but thinking about the CMEs, coronal mass ejections, those are electromagnetic phenomena mainly. And so it's really something that has a magnetic field that it's going to have an impact on. So we have seen CMEs interact with comets. We've seen them strip the tails off of comets. We've seen what we think is a magnetic reconnection happen in a comet, but we don't think asteroids have these kinds of magnetic fields. They don't have the coma, they don't have the plasma structure. So more than likely that sort of interaction will not happen. But we could be wrong, and we'll have to wait and see. But more than likely, no.
Thank you.
Don't be shy.
Now, I've never heard of any meteorites being radioactive, but which seems strange to me, that you haven't heard of, that I haven't heard of any. Is there any concern that any of these asteroids would contain radionuclides that are more powerful than, background type radiation?
Well, there isn't any enhanced radiation background in meteorites. Everything, though, has a radioactive signature. It's just how strong it is. I don't know, we have a meteorite expert over here, Jeff Grossman. Do you have anything to add to that?
So meteorites sometimes, or always, contain a little bit of enhanced radioactivity from what we call cosmogenic nuclides. These are caused by interactions of energetic particles with the surface of the meteorite in space. But the levels of radioactivity are so low that you need special equipment just to detect them. So no, there's no hazard.
I've heard that multiple meteorites hit Earth every day. I was just wondering, do they ever collide with our own satellites that orbit around us? And if so, is that something that you all help track and handle?
Well, yes, that's exactly right. There's over 100 tons of material that falls to the Earth every day, dust from space. We do track a hazard of meteoroids impacting spacecraft. We have an office at Marshall Space Center, the Meteorites Environments Office, that monitors the flux of meteoroids to the planet to determine if there's any enhancement of what we call the background flux, the stuff that happens every day. And during large meteor storms like the Leonids, there is some concern that spacecraft could be hit. There's several incidents over time where we believe a spacecraft may have gotten hit by a meteorite. It's a little difficult to prove until you go up and look at it, but we certainly see the weathering, I will call it, of the space station, for instance, getting hit by small meteorites.
There's even some dings in the windows of the space station. You have to remember even small pieces of dust traveling at really high velocity can actually, so we keep a close eye on it. No, the space station was designed to withstand that, obviously it can't withstand huge particles, but it was definitely designed to withstand these very small dust impacts. But we keep a close eye on it no matter
We
what.
actually saw an impact on MMS. The boom, the little tiny boom sticking off actually got hit.
So we're going to take one more question in the room, and then we're going to go to social media, and then we'll go back to taking questions in the room.
Generally speaking, do we know the composition of most asteroids, or do you expect to find possibly new materials on there? I mean, we're not looking at like unobtainium kind of thing, but do you expect to find new materials on it?
Well, I think that's the whole reason why we have missions like OSIRIS-REx, to go out and see what we really know about asteroids. We see the meteorites on the ground. We are reasonably certain they came from asteroids, comets, that were in orbit. So we know what we see from meteorites, but is that totally representative of the composition of these objects? So that's why we need these space missions like OSIRIS-REx to go out and sample and determine what all is there.
I can tell you as a geologist, there's nothing that makes me more uncomfortable than a rock out of context. And, that's why OSIRIS-REx is such an exciting mission, because we don't know what we don't know. And so to actually be able to understand, here's the context from which we got this rock, we now understand, is, for a geologist, everything.
Okay, Emily, do we have questions from social media?
Yeah, we have a couple from social. This first one is asking, will the public be able to track OSIRIS-REx when it's in space, and if so, how?
Jeff, is this a question that you can help cover?
Eyes on the solar system.
I was going to say, eyes on the solar system.
There's a really wonderful program that it's called NASA Eyes. And there are a number of different, it's a site that you can look and see where all of our spacecraft are in real time, and the graphics are really, really lovely. So it's actually divided into sections. There's Eyes on the Solar System, and Eyes on the Solar System allows you to see exactly where all of our solar system resources are. There's also Eyes on Earth, where you can see all of the different satellites, and there are something on the order of 30 different satellites that are orbiting the Earth and returning data. And then there's also Eyes on Exoplanets. And the Eyes on Exoplanets, I mean, unfortunately, we have no NASA spacecraft out at exoplanets at the moment, but what you can actually do is download an atlas of the sky. And you will see, especially with the Kepler data from the Kepler spacecraft, you will see exactly how many planets we know of around each star, and you'll see their proper configuration, the angle of the solar system, and where those planets are as far as we know. So NASA Eyes is a way that you're going to be able to tell minute by minute where OSIRIS-REx is and what it's doing.
Awesome, thanks. This next one asks, what is the most critical thing when working with asteroids?
Well, in my job, it's knowing where they are. We got to find them first before we can do anything about them, whether it be protecting the Earth from impacts or utilizing them as a resource in the future. The idea that there may be materials on asteroids that may be of some value, at least for exploration of the solar system, is another area that we work with. But you got to know where those objects are. So to me, it is knowing where they are, doing the observations to build up the catalog of where all the objects are and where they're going.
Okay, we're going to take one more question for social media, and then we're going to go back to the room for questions.
Okay, this last one asks how OSIRIS-REx specifically will help us for future manned missions to an asteroid before manned Mars missions.
There's a number of different ways, but one of the things I think we certainly learned, for example, from the Rosetta mission is proximity operations around small bodies are interesting, and NASA's gotten very skilled at going to Mars, going to Saturn, and doing, with the Cassini spacecraft and doing really complex maneuvering through a multi-body system. But proximity operations around a very small body are going to be fun and interesting, and I think that's one of the things that we're really going to learn from OSIRIS-REx is how to do that. And if we want to eventually land, say, humans on an asteroid, on one of the moons of Mars, Phobos or Deimos, these are things we need to learn, and so OSIRIS-REx is a key part of that.
Hey, good afternoon. So I recognize that NASA is more of a research scientific body, obviously, but I'm surprised we haven't heard any of the potential commercial ramifications of these are major leaps forward in things like asteroid retrieval and bringing planetary bodies into Earth orbit potentially, or being able to move them around. That seems like there'd be some interesting ramifications for commercialization of space. Is there anything you guys want to talk about that?
Well, certainly there's a lot of interest out there of the Earth is a finite place. We only have so much of, rare earth element minerals that, we are constrained. And obviously, as a society, we're having to learn that it's certainly important to live sustainably and try to reuse and recycle what we have. So right now, when we say, okay, are we going to run out of something? Would we need to go to our moon? Would we need to go to asteroids? Right now, the economics just isn't there. But will it be in the future? And so if we get to that point in the future where we say, okay, we can't live without a certain element, it's been depleted on the Earth, we need to go out, learning how to do proximity operations around small bodies, learning how to bring them back closer to the Earth, their ability, potentially we've even discussed, as you move humans further out into the solar system, do you bring everything from Earth? Do you use asteroids as a way to help resupply you as you go? These are huge questions we have. So the more we learn from missions like OSIRIS-REx, it helps you sort of put that into the trade space and say, money-wise, is this logical? It might not be today, but 30, 40 years from now, it might be. So let's learn.
Hi. This mission that you mentioned that actually retrieves a boulder from an asteroid, is that the follow-on mission to OSIRIS-REx? And is there a set timeline for that?
Well, I wouldn't call it a follow-on mission to OSIRIS-REx. As I said, it's a capabilities demonstration mission for human exploration, and our journey to Mars to develop the solar electric propulsion, high power, high thrust technology to take cargo and habitats to Mars. It's separate. OSIRIS-REx is a science mission done by the Science Mission Directorate, science-driven, whereas ARM is a technology capabilities mission for the future. But it is on a development path where it would launch in 2021, December 2021 is the date that it is being planned to rendezvous with the asteroid a couple of years after that. Spend about a year total at the asteroid, and then it takes about a year and a half to bring the boulder back to lunar orbit. And so the crewed mission to go up and sample the asteroid would be in the 2026 timeframe.
So it's fascinating to me that these bases that form really the basis for RNA and DNA are found on these asteroids and comets. Do we have a reason why the ones that we use in RNA and DNA are present? Are they the most frequently found ones on the asteroids that we've examined, or does it appear to be more by chance?
There's a little bit. One of the things is, does this say something about the conditions of the early solar system, that some of these were selected and some of these weren't? In terms of amino acids, I think for those of you that were in the last briefing, you heard Danny Glavin, who I absolutely love, and Danny was saying that actually only a subset of our amino acids are common on meteorites, that there are amino acids that are here on Earth that we think may have developed afterwards, so things that actually chemically developed after the original organics were brought. So there may be sort of amino acids that are older and those that are younger, which is kind of fascinating in its own right. And then there's the whole topic of chirality, because we only use, we immediately cut off half the amount of amino acids. So if you think about your hands, they're mirror images of each other, and there are molecules, there are amino acids that are also mirror images, but we only use the left-handed ones. And we actually, there is some suggestion now that there might be a slight overabundance of left-handed amino acids in meteorites. Why that would be is something that has astrophysicists very interested, because we're wondering if there might have been some kind of strong magnetic field around the formation of the early solar system. Is it possible that we passed near a neutron star or some object that was very, very strong magnetically, and it basically polarized the material that was in the early solar nebula? This is conjecture right now, but this is why we're looking for more clues. And as to exactly which nucleobases we chose, I'm an astrophysicist. I'm not actually an astrobiologist, but from an astrophysics perspective, I think there might be something really interesting here about what happened to our early solar system. So does anybody have any say about the particular nucleobases? I don't know the abundances myself. But the thing that really gets me, right, is if we're trying to find life on Mars, and we're trying to design these experiments to look for organics and look for organic processes, what if it uses entirely different nucleobases than what we have? And the amazing thing is that at NASA, we're trying to mimic that in the lab. We're trying to figure out what's in these meteorites, what sort of chemical combinations they might actually create, and how you might recognize the whole process of life is limiting the chemicals that you use. That's really fascinating. So people like you met, like Danny. Danny's one of my superheroes, and he's somebody that the careful chemistry these people do, as well as the creativity about what kind of life could you get with different nucleobases? What might it look chemically? I think that's one of the more exciting things that's happening at NASA right now.
Because you're only getting like a handful of material from OSIRIS-REx, how much testing can really be done with that amount of like amino acids and different materials that you pick up?
What is exciting is the amount of testing that you can do with material that you bring back here to Earth is so much more than you can ever hope to do with the spacecraft. So, we have mass spectrometers that we take into space that are, yay big. The ones here on Earth would fill, a quarter of this room. And so with very small amounts of material, you can do such precise analysis that we get amazing amounts of information. So we don't really feel we're inhibited. Obviously, geologists, we always want more rocks, the better. But because our instruments here on the Earth are so sophisticated, we'll be able to really wring the science out of that material.
Yeah, if they get as much as they plan, they're only going to use 20% of it, and they're going to put the rest of it away and keep it for the future.
Okay, and that's all the time we have for today's panel. I hope you guys learned as much as I did. For those who still have questions, please feel free to stay after and talk to some of the folks, or send them in using the hashtag AskNASA. For more information on all the stuff we do, go to www.nasa.gov. Thank you.